So anytime we're dynamically allocating memory, so let's look at this program again. Here what we're doing is we're dynamically allocating memory. And then before the program terminates, we delete X pointer. And what delete is doing is it is deallocating the object that X pointer points to. Then when we leave the scope of main, the statically allocated pointer is deallocated. But in C++, the programmer is responsible for deallocating any object that's dynamically allocated using new. So a simple way of saying this is that for every new, there has to be a corresponding delete. It sounds simple, but it's actually quite complicated because, here we have, the allocation and the deallocation is just one or two lines apart. If you have a complex program, it could be running for days or weeks, and then it becomes much more complicated when a corresponding delete should occur. But we'll learn some tools how to handle that, and a lot of it just has to do with very good coding practices. So there are two things that can happen that we'll call memory leaks. First of all, we can forget to deallocate a dynamically allocated object. So let's take a look at this. Actually, what I want to do is I want to copy pointer 2a to pointer 3a.cc. Let's do that. So what I'm going to do here is I am going to run this, and I'm not deallocating the integer. Now when I run this, it's going to look just fine. I mean, there's no indication that I've done something wrong. There's a program called valgrind. This is called a leak checker. First thing I have to do, and what valgrind does is valgrind tells you if you've allocated something that you forgot to deallocate. It can even tell you if you try to deallocate the same thing twice. So it's a very handy program. And in order to use valgrind, I need to compile by turning on debugging information. And I do that by using the -G switch. So I'm going to recompile my program. And now there's symbolic debugging information in the executable, and valgrind can use that. To use valgrind, I simply type valgrind, I give it the name of my executable, and it runs. And it tells me that in use at exit, I've got 4 bytes. And it tells me that I definitely lost 4 bytes in one block. So one thing I could do at this point is I could do leak check full, and then I could also rerun with the -V option. Let's run it with leak check is equal to full and see what that gives us. And now what I'm seeing here is it's telling me that it doesn't tell me where I should have deallocated it, but it tells me where the object was allocated. And now hopefully I can look at what was allocated and I can figure out, well, that should have been deallocated at some point. So let's go look at line 9, and you can see that this is where I allocated the object that was left in memory when the program terminated. So now if I go back and I deallocate properly, and I recompile again with the -G switch, and now I'm going to run valgrind again, and now it tells me that in use at exit I had 0 bytes, and it tells me that I have no errors and no contexts. Okay? So this is how valgrind can at least tell you that something is wrong. Now the other thing that can happen is, let's say that I allocate something here, and then I allocate something else at a later point in the program. I'll do it down here. Right. So look what I'm doing. I'm creating a new integer 5, and I'm making X pointer point to it. So when the program executes, I'll see 5. And then I'm creating a new integer 10. Well, I didn't deallocate the integer 5, so it's still left in memory. I don't have access to it. This time I'll print 10. And when I delete X pointer, I'm only deleting the integer 10. I'm not deleting the integer 5. In fact, the integer 5 remains in memory, and Valgrind will tell us that. Now, the execution of the program looks exactly the same. I'll print 5, I'll print 10. There's no indication that something is actually wrong. But Valgrind will tell me that I definitely lost 4 bytes in one block. Okay, and notice here that I've got 2 allocations, but I only have 1 free. So in order to fix this problem, I have to go in, and yes, I have to delete X pointer here. I also have to delete it here. When I'm finished using the integer 5, I have to delete it. I can reuse X pointer and make it point to a different integer if I want to, but I have to make sure that I deallocate the integer it previously or it's currently pointing to before I move it. And that's another example of a memory leak. So now when I run this, again with the -G option, I get the same output, 5 and 10. Valgrind tells me that I have not lost any memory. Same thing happens with class objects. So if I make a copy of pointer 2b.cc to pointer 3b.cc, I can do the same thing here. Let's say, for example, that this delete is not here. I'm going to get rid of this statement. And Valgrind is going to tell me, so the program is going to execute just fine, just like before, but now Valgrind is going to tell me that I lost some memory, that I left some memory deallocated. There were objects left in memory that were not deallocated. So that's the output I expect, and now when I run Valgrind on a.out, you see that I lost 8 bytes. Well, where do we get 8 bytes? Well, each integer is 4 bytes. So in the previous example, I left 1 integer in memory. That's why I lost 4 bytes. Now a point object consists of 2 integers, and that's where I lose 8 bytes. So now if I go back in and I replace or I uncomment the delete statement, I recompile this and I run it, I get the same output, but this time when I run Valgrind, it tells me that I had 1 allocation, I had 1 free, it deallocated 8 bytes. Those are the 2 integers of the point object, and you can see that I have no errors. That's what we want.